Welcome to video 1 for section 6.7, where we'll be dealing with exponential and logarithmic models and some data fitting. So we're going to practice modeling exponential growth and decay. We're going to talk about logistic growth models, and then we're basically going to look how to choose an appropriate model, express an exponential model with base E, and fit model to data. All right, let's talk about exponential functions, just to kind of remind yourself where we came from. There are 8 characteristics of the exponential function a of t equals a sub 0 e to the kt, which is what we're going to be used to model exponential growth and decay. First of all, it is a one-to-one function, so it passes the horizontal line test. It has a horizontal asymptote at y equal to 0. The domain is all real numbers. The range is from 0 to infinity. There are no horizontal intercepts, and the vertical intercept will happen at 0, a sub 0. So a sub 0 is really our initial value if we're thinking about a modeling situation. It's going to be exponential growth if our rate value is greater than 0, and it's going to be exponential decay if our rate is less than 0. Let's use an example with this model. Let's talk about doubling time of bacteria. A population of bacteria cells doubles every hour. If a certain culture started with 10 bacterial cells, find a model that gives the population of bacteria as a function of time. The model we're going to use for exponential growth is going to be, let's copy, I think they use A, right? A of t. I used P before, so it's weird to use A, but that's fine. I think the book uses A. A of t equals a sub 0, and the sub 0 notation is really what mathematicians and scientists use to designate an initial value. A sub 0, anything with sub 0 is your initial value, e to the kt. So this is the model that we're going to use for this situation. Well, the first thing that we can read is that the population of bacteria doubles every hour. That's important information. And if a certain culture started with 10 bacteria cells, find the model that gives the population of bacteria as a function of time. So right off the bat, we can write down a couple of data points. We know that at time equal to 0, there was 10 bacteria cells because they said that it started with 10. And they also told us that it doubles every hour. So after 1 hour, our population is going to be at 20. All right? And these two data points are enough for us to figure out this model. Let's plug in the first one. T equal to 0, a of t equals 10. So the first one is 10 equals a sub 0, e to the k times 0. Time is 0, amount is 10. E to the k times 0 is e to the 0. E to the 0 is equal to 1. So this is just a sub 0 times 1. And so really that tells us that 10 equals a sub 0. Now we don't have to work through that again, because now we know that if we're given the y-intercept value right here, we can plug that straight in for a sub 0 without any work, because the e to the kt part is always going to be equal to 1 if we have that exponent equal to 0. All right, so now our model looks like a of t equals 10 e to the kt. We need to figure out the value of the parameter k, the growth rate for this model. And we're going to use our second data point to figure that one out. So the point 120 is going to help us figure that out. So let's plug in the point 120. So 20 is our amount. That's equal to 10 e to the k times 1. Now that does not look like a k. Let's write that more neatly. K times 1. So that's the same as 20 equals 10 e to the k. Solve this for k. Divide each side by 10. We get 2 equals e to the k. This is an exponential equation. We know how to solve these. To get that k out of the exponent, we take the natural log of both sides. Natural log of 2 equals the natural log of e to the k. Use our exponent rule, and we get natural log of 2 equals k times the natural log of e. The natural log of e is 1, right? Natural log of e is 1, so natural log of 2 is equal to k. Since this is a story problem, we are allowed to use decimal approximations. So let's get a decimal approximation for the natural log of 2. And it's about 0.693. So I'm going to use k equal to 0.693. So my finished model is a of t equals 10 e to the 0.693 t. And there's my model for this situation. If we want to check our 2 points, we can. If we plug in 0, we're going to get 10 because e to the 0 is 1. If we plug in 20, we can take 0.693 times 20, exponentiate e to that power, multiply it by 10, and I did something terribly wrong. Let's try that again. 0.693 times 20, oh no, times 1, dear Lord, times 1, raise e to that power, multiply that by 10, and sure enough, I got 19.997. So we definitely got our point output value of 20. All right, so there's how we model exponential growth, given some information about the model. Let's talk about half-life, or exponential decay. Half-life is the amount of time it takes for something to decay to half its previous amount. So let's say we started with 100 grams of a substance that has a half-life of 2 days. So 0 days, we'd be at 100. 2 days later, we'd be at 50. 2 days after that, so 4 days after originally would be a half of 50, which is 25. You see how this goes on, 12 and a half, et cetera, et cetera. We're never going to get down to nothing, which is what makes this really useful for carbon dating, because there's, when you find artifacts, you can see how much carbon-14 they have and use that to decide how old something is, which is what we're going to do right now. It is true that after 5,715 years, a given amount of carbon-14 will have decayed to half its original amount. So we're going to find the exponential decay model for carbon-14. So the half-life is 5,715 years. All right, let's write down a model that we're going to use. Same one, A of t equals A sub 0 e to the kt. We're going to use this half-life information. So let's just say we have 100%. This is how I like to think about it. So I'm going to start at time 0. I'm going to have one whole amount of carbon-14. And then 5,715 years later, I will have half that amount. All right? Remember, my first value is my time, and my second value is my amount. And these are my two values. I'm just saying one. You could say 10, you could say 100, and then adjust the next one to be 5 or 50. But I'm going to say my amount is one whole unit, and that means that I will have a half unit 5,715 years later to find my model for exponential decay for carbon-14. So if we plug in 0, that means A of 0 equals 1 equals A sub 0 e to the 0. And remember, I told you guys we didn't have to do this anymore. I lied. A sub 0 equals 1, right? So now we know that A of t equals 1 e to the kt. So we don't even have to write that 1 there anymore. That's why I picked 1. Let's plug in our second point, which is t equals 5715, and the amount is 1/2. 1/2 equals e to the k times 5715. We need to solve this exponential equation using a natural log. So the natural log of 1/2 equals the natural log of e to the k times 5715. Using our property of exponent rule, this brings us down in front. We have natural log of 1/2 on the left-hand side, and on the right-hand side we have k times 5715 times the natural log of e, which we hopefully by now know equals to 1. So all we need to do is divide each side by 5715. And I got k equals natural log of 1/2 over 5715. Since this is a story problem, I'm going to get a very good decimal approximation for this. So we take natural log of 1/2, and we divide that by 5715, and I get k equals, and remember this is decay, so we're expecting it to be negative 0.000121498. 1498. And I'm actually going to go ahead and write that all down, just because I want this to be as accurate as I possibly can. Now that's not a perfect approximation. That's just as accurate as my calculator will go. All right, so my model is A of t equals 1 for A0 e to the negative 0.000121498 t. There's my model. You probably don't need to use it in new decimal places. I just like to. All right, now that we have this great model for carbon-14, let's go ahead and use it in a story problem. In 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab herdsman. Analysis indicates that the scroll wrappings contain 76% of their original carbon-14. So we're going to estimate the age of the Dead Sea Scrolls by using our model we found in part A. Let's rewrite it down here. Our model was A of t equals E to the negative 0.000121498 to the t. So we're going to use this to estimate the age. Well, we know if there's 76% remaining, that if we started with one whole amount, we now have 0.76 amount. So we're going to put, this is the point t, we don't know, 0.76. We have 76% of the original carbon-14. So I'm going to put in 0.76 is my amount. And that's another reason why I picked my initial amount to be 100%. That way, if you know what the percent that's remaining, you can just use that percent as a decimal. Equals e to the negative 0.000121498 t. All right, how do we solve this equation? It's an exponential equation. It's got a base of e. Let's take natural logs of both sides. Natural log of 0.76 equals the natural log of e to the negative. I'm kind of regretting using this many decimals, but I'm sticking with it because I've come this far. All right, my property of logs brings this all down in front. We know the natural log of e is 1, so we get natural log of 0.76 equals negative 0.0001211498 t. So we're going to divide both sides by that number. And we're going to get a value for t. So let's take the natural log of 0.76 and divide it by negative 0.0001211498. And I get t equals 2,258.78. So 2,258 years old. Or were 200,258 years old. Well, I should say 259, huh? It rounds up. In 1947. All right, let's stop this video for now and we'll continue in the next one.